Hello and welcome back to my channel. On this video, we'll be looking at the third example on MSTs. If you have not subscribed to this channel, please do subscribe and like, comment. So I would like for you to pause this video, read up the question and get right back. For the first question, we want to determine whether every minimum bottleneck tree of a graph is a minimum spanning tree of that graph. We want to either prove it if it's true or give a counter example if it's not. And for this A question, it is not true, and we'll be giving a counter example. And to explain this, it's not true because every minimum bottleneck of a graph is not necessarily a minimum spanning tree of that graph. And this is so because a minimum bottleneck focuses on minimizing the most expensive edge in the spanning tree. The criteria is different. The criteria for bottleneck is on the costliest edge. So we want to minimize the most expensive edge in the spanning tree, while the criteria for a minimum spanning tree is to minimize overall cost of edges. We want to minimize overall cost of edges on the tree. Before we actually start to write something, I need you to take note of this definition. In the question, it says a spanning tree T of G is a minimum bottleneck spanning tree if there is no spanning tree of G with a cheaper bottleneck edge. We can say that a tree has minimum bottleneck, or it's a minimum bottleneck spanning tree if there is no other spanning tree from the graph that has a cheaper bottleneck edge. So we're going to take our counter example. Let's consider this graph. We have a graph with edges. Let's call this edge E prime. And the cost of this edge is 100. We have another edge. Let's call this edge E star, and let's call this edge E. And we have a cost of 10 and 10 on both E and E star. Let's find different spanning trees from this graph. Let's take our first spanning tree with 100. That's E prime and E star, 110. So we're going to call this spanning tree T prime. And it is a minimum bottleneck tree because there is no other edge in this tree whose cost is cheaper than the most expensive edge, right? Okay, so let's look at another tree. Let's take 100 again. That's E prime and E, which is 10. And we're going to call this T. So we see that in as much as they are different spanning trees, the both of them are minimum bottleneck trees. T and T star are minimum bottleneck. They are minimum bottleneck trees. But then let's consider another example. When we remove 100, we have this other tree, 10 and 10. That's E star and E prime. And this is an MST. Let's call this some MST T prime. Let's call this T prime. So this is an MST. It's a minimum spanning tree because the both edges, it is the cheapest edge. It has the cheapest edge from this given tree. It has the cheapest total edges from this given tree. So every minimum bottleneck tree of G is not a minimum spanning tree of G. Like I said earlier, the criteria for the definition of minimum spanning tree, that's our MSTs, and minimum bottleneck tree, minimum bottleneck spanning tree, is not the same. one concentrates on minimizing the most expensive edge. That means you should have a most expensive edge, and it should be the cheapest expensive edge, while the other one, MSTs, concentrates on minimizing the total edges of the tree. Let's move on to question B. So for question B, we want to find out if every minimum spanning tree of G is a minimum bottleneck tree of G. We want to prove or give a counter example. Let's go through that real quick. What do you think the answer should be? Have you thought about it? So for this question, the answer is true. It is true that every minimum spanning tree is every minimum spanning tree of some graph G is a minimum bottleneck of that graph G. And that's because in a minimum spanning tree, we have the cheapest edge of the tree, and every other edge cannot be cheaper than the edge of a minimum spanning tree. It's just like in the example we gave for the MST, where you have two edges, 10 and 10, with cost 10 and 10. We don't have any other edge cheaper than that. So that's a minimum spanning tree, and also in itself, it's a minimum bottleneck tree. So like I was saying, in a minimum spanning tree, we have the cheapest edge of the trees, and every other edge cannot be cheaper than the edge of the minimum spanning tree. This implies that every other edge is more expensive. The edge of the MST is the least expensive. So the MST is a minimum spanning tree. The MST, which is the minimum spanning tree, is the minimum bottleneck tree. Now let's for this case we are going to prove, because we said it's true. So let's start by drawing a subset of vertices. This is S and V minus S. So we have some connections here, Let's say we have our cheapest edge, and let's call this E, right? So with this cheapest edge, let's call this tree T. So we have a T, which is the MST. We have E goes from V to W, where V is an element or a vertex in S, and W is a vertex in V minus S. So we say that the edge E of T is also a bottleneck edge, since no other edge is cheaper than it. Supposing, let us consider another spanning tree, T prime, whose cheapest edge is E prime. Let's, for a second, imagine that we do not have E, and we have another edge, E prime, which gives us another spanning tree, another minimum spanning tree, T prime. But E prime is greater than E. So what does that mean? It means that if we want to find the MSTs, considering these two trees, different trees from the same graph, right? Imagine them to be, let's wipe this. Considering this instance, which is now T prime, and the first instance, which is T. If we want to choose the MST, we are going to discard this, because this is more expensive, and choose the graph with this, with E. And that's because the cost of E is less than the cost of E prime. And if that is so, it also implies that there is no other spanning tree in G with an edge cheaper than E. There's no other spanning tree in G with an edge cheaper than this one, cheaper than E. So this means that the edge of E is part of the minimum spanning tree, and that every minimum spanning tree of G is also the minimum bottleneck of G. And this is because no other edge is cheaper than E, which is the cheapest edge. We can also call it a minimum bottleneck tree. I hope this is clear. Your takeaway from this video should be that the criteria for defining minimum bottleneck and minimum spanning tree is not the same. One concentrates on minimizing the most expensive edge. The other one concentrates on minimizing the overall edges. So I hope this makes sense. Remember to subscribe, like, comment, and I'll see you on the very next example.